Okay, so in this video, we're going to look at a couple of examples of working with improper integrals. Improper integrals are integrals where either one of the limits is infinity or one of the limits produces lets the original function be undefined, or there is a point inside the middle of the region where you're integrating where the function is undefined. So in this example up here, we have one limit that's infinity. In this example, both endpoints have the integral that is undefined. And in this example, we have a point in the middle at x equals 0 where the integral is undefined. So all of these would be classified as improper integrals. And so we're going to look at slightly different strategies to deal with them. They basically come down to the same thing. If you have a limits of integration where both of them are undefined, then it's going to actually be very similar to the case where we have the point in the middle that we have to worry about. We're going to have to split the integral up and then proceed from there, because we have to treat each infinity separately. But we're going to look at an example where we just have one infinity first. Now, the general idea here is that infinity is not a number, and we shouldn't treat it like it's a number. And so fundamentally, what we're going to do is we're going to turn this into a limit. And then we're going to replace our integral by. Sometimes the copy and paste does not cooperate. Our limit is going to be replaced with a dummy variable, and then we're going to be able to complete the integration as normal. And then we'll worry about the infinity when we get to the end. So in this particular case, we are looking at integration by parts. So we're going to let u be x and du be, or dv be e to the negative x dx. And that means du is dx and v is negative e to the negative x. And so that's going to give us, again, another limit. B goes to infinity of negative x e to the negative x v du, or vu, and then minus a minus is going to be a plus, the integral of e to the negative x by itself. And again, all of this is inside the limit, and these ones are technically being evaluated from 0 to b. So just be really careful about the notation. And finally, we can evaluate our last integral. And this e to the negative x becomes negative e to the negative x. And again, we're evaluating it between 0 and b. And so when we plug those things in, we're going to end up with b and b and b and minus 0 e to the 0 minus e to the 0. So this is 0, obviously, and this is 1. So that's great. So we've got 1 plus something. So this becomes plus 1. And so then the real question is, what happens when we let b go to infinity? So when b goes to infinity, e to the negative infinity, that's going to be 0. So that's going to disappear on us. So that's good. So that's going to be 0. And so now we're just left with this. And for this one, again, technically what we're doing is we're doing L'Hopital's rule. So we can think about it this way. This is going to be e to the negative b, like so, e to the b rather, in the denominator. And again, the plus 1 doesn't do anything. We want to know if this is going to converge or diverge. So if we apply L'Hopital's rule to this expression, again, the 1 is not really going to do anything for us. And so, in fact, I'm going to put the 1 plus out front so we can happily ignore it. And then applying derivatives, the derivative of b with respect to b would be 1, and the derivative of e to the b with respect to b would be also e to the b. And so that's going to go to 0. And so this will converge to 1. So with an improper integral, we say that this converges because we get a finite value. If it fails to result in a finite value, if the limit doesn't converge, if it goes to infinity or is undefined, then we would get divergence. But again, the idea here is that infinity is not a number. We can't just say e to the infinity. That's not mathematically accurate. And it's not so much, and it's not that the original function is infinity or not, because as we'll see in some of these other examples, the original function may be undefined, but they won't necessarily be undefined after you integrate. And so it's the after you integrate function that needs to be evaluated in the limit. So again, we have a similar issue here at the second example. Both of these endpoints are undefined. And so what we can do is we can separate them out. And what we're going to do is we're going to essentially create 2 separate integrals. And we're going to do a similar process here. Again, we want to treat improper integrals, separate limits separately. So we're going to have one of these is going to have a limit. I didn't really want to do that, but we're going to say this is the lower limit first. We're going to let the lower limit go to -1. And then our integral will go from a to any point in the middle. Pick something that's easy to work with. And then the second one, again, will be very similar, except that I'm going to use a different letter to go to the other endpoint. And your second integral will pick up where the first one left off. So this is a case where you have 2 integrals that are both problematic. Again, if you have 2 infinities, infinity and negative infinity, you would do the same thing. You would have one value go to negative infinity, one value go to positive infinity, and split it again, usually at 0 because that's a convenient value. And then you do your antiderivatives. In this case, both of these antiderivatives are going to be arcsine. So this will become arcsine x, and we don't need the dx, and evaluated from, oops, I didn't mean to do that. from A to 0. And then same thing is going to happen for this one. Except we're evaluating it from 0 to B. Now, when you put all of these together, then you're going to end up with hopefully something that evaluates appropriately. So let's see what happens. Arc sine of 0 didn't work very well. Sine of 0 minus arc sine of -1. Again, our limit negative of A. And then same thing here. This will become arc sine of B minus arc sine of 0. Now, arc sine of 0 is 0, so that will reduce considerably in both cases. Arc sine 0 and arc sine of 0. And so then we just have to evaluate what happens when we plug in arc sine of -1. And arc sine of -1 is perfectly well defined. What angle gives you sine of -1? And it's going to be -pi/2. And with the negative in front of it, that's going to give you just pi/2. And then arc sine of 1, again, perfectly well defined. What's not going to give you? That's also going to give you pi/2. And so we're left with pi. So in this particular case, everything was just able to be evaluated. It was undefined at the limit in the original problem. But once you did the antiderivative and you plugged in your 1 and your -1, you got perfectly well-defined values. And we were able to find an integral that converges. Now, for the last one, this one it's perfectly well defined on the ends. These ones sometimes are a little harder to spot. The problem is actually in the middle. The problem is at 0. So what we're going to have to evaluate this at is as if we were going from -1 to 0 of 1 over x squared, or x to the -2. And then from 0 to 1, x to the -2. But the problem point is not at the 1 and -1. The problem point is at the 0. And so what we're going to do, again, is we're going to apply limits. And again, what you call them is not particularly important, but you should use different values for different integrals, because they don't have to be the same thing at the same time. Zero. And then this will be B, and this will be A. Now, again, doing the anti-differentiation here is not a big deal. you're going to end up with in this case, you're going to end up with -1 over x, and the limits are going to plug in as -1 and b, and then same thing here. You're going to end up with -1 over x, and the limits that you'll plug in will be a and 1. And again, the ones are not the issue. The issue is going to be what's going on when you plug in the zeros. And so let's see if they'll let me delete a bunch of this without, nope. B goes to 0, and when we put in b, we get -1 over b minus -1 over -1. And again, the 1 here is not a big deal because it's a finite value. What we care about is what's happening when we plug in the 0. And then similarly, the limit as a goes to 0 of, now here it's -1 over 1 minus -1 over a. And each of these limits has to be evaluated separately. So the fact that like this one, and again, you can think of b is coming in from the left, and a here is coming in from the right, because our values might be positive or negative infinity. Again, it doesn't particularly matter in this particular scenario, because even if they are technically opposite infinities, they're not allowed to cancel out, because each side of the integral has to converge or diverge separately. If either of them diverges, then the whole thing diverges. So 1 over 0, it doesn't matter whether it's positive or negative infinity, it is infinity. And so the fact that this one is also positive or negative infinity, we do not have to evaluate the signs, because infinity minus infinity isn't necessarily 0. And so it's not necessarily any finite number at all. It could still be infinity. And so what we would say is that this integral diverges. So again, that's sort of the trick with these, when you have to worry about both endpoints, both halves have to converge. We saw that with the arc sine issue, they both went to a finite value, and so we were able to evaluate them. But even if you have an example where one of them converges and one of them diverges, it diverges. And if they both have infinities in them, again, you don't have to evaluate the signs, because they can't cancel each other. If one half of it diverges, the whole thing diverges.